Before we go too far into this topic 5, we need to go back and we need to review some of the laws of powers or indices that we looked at earlier. By the end of this topic, we'll have a look at these problems, these 3 problems, and we'll go over them. In the meantime, you just need to know that exponents and powers are very important to engineers and scientists. Recalling from topic 2, a to the power of m times a to the power of n, you add the powers. When you're dividing, you subtract the powers. When you take a number that is to a power and you raise that to a power, then you multiply the powers. So let's have a look at these examples. X squared, y cubed, all to the power of 4. That means everything has to be raised to the power of 4. So it would be x squared to the power of 4. That would be x to the power of 8. And y to the power of 3 to the power of 4. 3 4s are 12. The top line on this, x to the power of 3 to the power of 4, becomes x to the power of 12 over x to the power of 2. This is now a division sum, so we subtract the powers, so it would be x to the power of 10. Again, recall from earlier that a to the power of negative m is 1 over a to the power of m, and a to the power of m is 1 over a to the power of negative m. So if we're going to look at 2 to the power of negative 5, 2 to the power of negative 5 is 1 over 2 to the power of 5, and we could work it out if that's what we needed to do. 1 over 3 to the negative 4 becomes, it's an example of, no, it's an example of that one. So it becomes 3 to the power of 4, and it may well or may not be important to work out the actual number. Right, using those rules, 1 over x to the negative 9 will become x to the 9. X to the negative 2 times x to the 7, you're going to add the powers, so that would be x to the 5. X to the negative 3 over x to the negative 5, you're going to subtract, so it would be x to the negative 3 minus negative 5, so it would be x squared. This one will be x to the negative 15. And the last one would be 1 over x to the 4, 1 over x to the negative 4, which would become x to the 4. Now we look at powers of x that are fractions, and x to the power of a half we can rewrite as the square root of x, x to the power of a third is the cube root, and so on. So 81 to the power of negative a half is the same as 1 over the square root of 81, which is 1 over 9. Don't forget it possibly is plus or minus. 5 to the power of 2 to the power of a third. Let's do the bit in brackets first. That's 25, and then it would be the cube root of 25. 5 to the power of negative 2 to the power of a third. 5 to the power of negative 2 is 1 over 25, and then you want the cube root of that. And if it was important to you, you would find the number. We can have fractional powers. If you've got fractional powers of a number, you're just going to use your calculator. But if we've got a variable to a power that's a fraction, then we can't. We have to actually work it out. So the first one, that's a straightforward x to the power of a half. The next one, again, is straightforward. It's just the cubed root of y. The next one, similarly, it's the fifth, rewrite it as x to the 5th to the power of a half, which is x to the power of 5 over 2. The last one, it's 5 to the power of 7 to the power of a third, which is, sorry, 5 to the power of 7 over 3. If we've got a function of the type f of x equals a to the power of x, and a is, some positive constant and x is some ordinary variable, then we call these exponential functions. So that is an example of an exponential function. However, we need to be a little bit more sort of interested in things than just 3 to the power of x or 7.5 to the power of x. We need to look at a specific one. So these 3 to the x, 7.5 to the x, they are just what we call exponential functions. But then in engineering, we get many functions that are written in terms of this e. Now, it's not a letter, it's actually a number. It's Euler's number. And we will use it a lot. If it's just e, it's e to the power of 1, and we could look that up on our calculators and find that that was approximately equal to 2.7182812828, etc., etc., etc. It behaves exactly the same as any other number in terms of powers. So we can talk about e to the power of 1, we can talk about e to the power of 2, talk about e to the power of x, and it uses the same rules as before. So you could do something like e to the power of x squared, and that would be e to the power of 2x, and so on. So it uses exactly the same rules as any other exponential function, but it is a very special number. We can graph exponential functions, but what we find is the larger this number here is, so the larger the coefficient of x, the steeper the curve. And the steeper the curve, that means the faster that y is growing. I need to remember a few of these. Have a look at this first one, y equals e to the x. What it's saying as x is getting bigger and bigger, e to the x is also getting bigger. They're going to cross, you need to look at when x equals 1. No, in fact, we need to look at when x is equal to 0, then y is equal to 1, because e to the power of 0 is 1. Compare those. Some of these have got decimal powers, some of them have got numbers in the front. The number in the front there is going to correspond to where it cuts through the y-axis. Similarly, this one has a third in the front, and that's going to be where it cuts through there. A couple of standard ones, a little bit of difference. Look at that. That's got an a in it, and we're going to end up with an asymptote at y equals a. The graph is not going to cut the line y equals a, but it's just going to get closer and closer and closer to it. A couple of examples: decay of voltage and the rate at which a body cools. You're given the expressions, now draw a picture and find a bit of information about it. Right. We know it's a decay curve, so it's going to have that typical downward shape. We also know that when t is equal to 0, v is equal to 250 e to the power of 0, which is equal to 250 times 1. The second question asks us to look at a curve where we're looking at the rate at which a body is cooling, and it's given by 250 e to the power of negative 0.05. Again, we need to give it a quick sketch. When T is 0, theta is 250. It's going to be, again, a decay curve like that. Now, this one, it asks you various things. It says when T equals 5, so you can read off it if your graph's accurate enough. If your graph's not accurate enough, then you're going to actually have to put it into the expression. And work it out using your calculator. Don't forget to give a unit. You're also asked to find when that's 25 minutes, so it'll be way over here. Like that. Again, you can read it off your graph, or you can just put it in algebraically. And working that out on your calculator, 71.63 degrees, which looks about right. That's 194, 195-ish, and that's 72-ish.